This lesson we're going to be looking at the different types of stationary points. So if we just look at a visual of any function, let's get a nice one like this, we can see that this point here would have a tangent that has a gradient of 0, as would this point here. So let's just call that A and B. So we know visually that at point A we have what's called a local maximum, because as it's going up, that turning point is the highest y value that it gets to before it goes back down again. And at B, we'd say we have a local minimum. Is a local minimum. Now, that's all well and good when we can see the graph in front of us. The other type of stationary point we can have is a point of inflection. So this point here, we'd say that can be point C. Right, C is a point of inflection. Now, what if we didn't have the graph in front of us? What if we just knew the original equation? How do we find it out? Well, if we look at these examples, A, B, and C here, we can see that to the left of point A, we have a positive gradient, and to the right, we have a negative. And then, oh no, we don't. Oh yes, we do. And then for point B, to the left of it, we have a negative, and to the right of it, we have a positive. And for point C, we have a positive and a positive either side. So if we look at the derivative for f of x, then for the local maximum, it has to be going increasing. So we have to have for f dash x, or the derivative of x would have to be positive, so it's greater than 0 to the left, and f dash x would have to be negative to the right for a local maximum. Okay, then for a minimum, we have the opposite. So we have, for a minimum, we'd have f dash x is going to be less than 0. It's going to be negative to the left, and the derivative to the right would have to be positive. So to the left or the right of the point we're looking at. So at point A, to the left of it is positive, and to the right of it is negative, so therefore it would be a maximum. For a point of inflection, then f dash x, or derivative of x, could be positive to the both on both sides, like we have in this example here, point C, or it could actually be going the other way. So you could have negative on both sides. Now, if you want to use the plus or minus signs, and positive, negative, you can. So in this case, we're saying negative, negative. Here we're saying positive, positive. And up here we're saying positive, negative. And then for the minimum, would say negative to positive. So I know my explanation relied heavily on this graphic on to the left. So let's look at an example where we don't know what the graph looks like. So we're asked to find all the stationary points for y equals x squared times x minus 4. So first thing, to find the stationary points, we find the derivative. So for a stationary point, find derivative equal to 0. So x squared, so I'm going to expand this out, x cubed minus 4x squared, so dy dx would equal 3x squared minus 8x. And so we can factorize that again. So let's take out x out the front, would get 3x minus 8. And so when we solve that equal to 0, therefore x 3x minus 8 equals 0, we end up getting x equals to 0, or x equals to 8 on 3. So the brackets being 3x minus 8, 8/3 would make that equal to 0. So there's our x values. So to find the stationary points, we have to sub those back into our original equation. And we can do that with this top one up here if we wanted to, or we can do the factorized form. So when x equals 0, so let's say at x equals 0, y would equal, what would that be? It's going to be 0. So that's one stationary point, and the other stationary point is at 8/3. This is where it gets a bit messier. We'd have y equals 8/3 all squared times 8/3 minus 4. And we can put that into our calculator, which would give us a, oh yuck, negative 256 on 27. So that's your other stationary point. So the last thing, we found our stationary points, there's only 2 of them. So we want to find, are they minimums or maximums? So min or max or point of inflection. So if we know the values 0 and 8/3, we just have to pick a value to the left and the right of those. So let's go at x, and we're going to find the derivative either side of them. So the ones that we know at 0, we know the derivative was 0, and at 8/3, because we've found those out, it's also 0. Then we just have to find to the left or right of it. So pick a number that is less than 0, and don't make it hard for yourself. Don't go negative 17. Let's go negative 1. It's a different color actually. So let's pick negative 1, and I'm going to pick positive 1. Alright, 8/3, think about that, it's just below 3, so we could just put 3 if we wanted to. So, dy dx was 3x squared minus 8x, or x times 3x minus 8. So at negative 1, we'd end up getting negative 1, let's go to y dx. At negative 1, you'd get negative 1 times negative 3 minus 8. So you'd get negative 11 times negative 1 is positive. So it's going to be positive y dx at positive 1 would be 1 times 3 minus 8, which would be 1 times minus 5 is negative 5. So that is negative there. Notice I'm not writing the answer because I don't give a stuff. Oh, hang on, I shouldn't say that because I don't, doesn't change the, or doesn't influence the answer. So positive or negative is all I'm looking for. Positive at negative 1, negative at positive 1, and then at 3 dy dx, at 3 I would have 3 times 9 minus 8. So I'd get 3 times 1 is 3. So that is positive. So if we look at this now, we just have to determine if these two stationary points are minimums, maximums, or points of inflection. So if it's positive to the left of it, that means you've got a gradient going up like that, and then it's negative that side, so therefore it must be a maximum. And the other one is going negative, so that means it's decreasing, and then it's positive on the other side, so this must be a minimum. Okay? Like I said, some of the calculations, the algebra might get a little bit trickier, but all we're looking at is it positive or negative on either side, and then helps you visualize it without actually sketching the entire graph. Okay, all the best for this is exercise 18D.